In this video now, we're going to introduce the idea of adding angular momentum. This came up because we learned in the last video that the only good quantum number once you turn on spin-orbit interaction in the hydrogen atom is the total angular momentum J, which is equal to L plus S. Okay, so this means that instead of having quantum numbers L and S, all that we have is J, which corresponds to the addition of L and S. But now, to go from the definite values we know about L and S to figure out what possible values we could expect for J, we need to know how to add up angular momentum. So how to add angular momentum comes down to, so the general question of how to add angular momentum boils down to saying that if you have two different values of J, call them J1 and J2, and these could be any different types of angular momentum, so J1 could be L and J2 could be S, or any other combination like that. So this boils down to asking the question, what are the possible values of J total that can be obtained from adding up the angular momentum that correspond to J1 and J2? So answering this in general for any values of J1 or J2 or any types of angular momentum, whether they be orbital or spin-based, is actually a very challenging question. But in our case, we can simplify this because we know that L will always be integer, and we know that S will always be 1/2. And so what we're going to talk about are just the rules for adding angular momenta in this particular special case, with L being integer and with S being 1/2. So when you combine angular momenta J1 and J2, the possible values of J total that you will get will generally be, so the lowest value you can get is the absolute value of J1 minus J2. You can see other values that will always be separated by 1 unit of angular momentum. So you see the minimum plus 1, plus 2, and so on, up to a maximum value of J1 plus J2. So if we let J1 be L and J2 be 1/2, because this is a spin, and this means that the possible values of Jt here, of total J, will always be absolute value of L minus 1/2 and then L plus 1/2, meaning there are only these two values. And we'll see in a moment why I'm writing it specifically as the magnitude of L minus 1/2. Okay, so for example, if we combine a p orbital with the s equals 1/2 electron. Okay, so p orbital has L equals to 1. So this means that we have two values of Jt we could produce. The first will be 1 minus 1/2, and the second one will be 1 plus 1/2. Right, so J will be either 1/2 or 3/2. And now let's somewhat verify this by doing a sanity check. Right, so we started off. So if we combined all possible p orbitals with all possible s equals 1/2 states of the electrons, those are 6 possible states, right? We have, for L equals 1, we have m sub L is equal to -1, m sub L is equal to 0, or m sub L equals to 1. So that's 3 different possible m values for the p orbital. And then you can have m sub s equals plus or minus 1/2 for s. And so if you can have, so you have this 3 times 2 different possibilities that you can have for different ways to combine L equals 1 and S equals 1/2 different states. Okay, so this means that we have 6 different states. And now if we combine them, right, we haven't changed the number of allowed states. All that we've done is we've reclassified them into whether they have a total angular momentum of 1/2 or 3/2. And so that means that the total number of states writing in terms of J should be the same as writing in terms of L and S. Okay, so we can write out all of the allowed m sub J values for each of these different 2 values of J and make sure that they add up to 6. Okay, so first we'll have Jt is equal to 1/2. And from this we know that m sub j can start at minus 1/2, and then it keeps going by plus 1 up until we get to plus jt, so this goes up to 1/2. Okay, so there's two values there. And the next jt can be 3/2, and here we know that mj can go from minus 3/2, keeps growing by increments of 1, so the next one being minus 1/2, and then plus 1/2, followed by 3/2, and then we've reached the end, or then we've reached j, and so this stops. Okay, so up top we have two states for the jt equals 1/2, and we have 4 states for the jt equals 3/2, and so combine those and you get, indeed, the 6 states that you expected. And you also notice that the number of states here follows the same degeneracy formula, so g of j, which is the degeneracy of the number of states that are allowed with the same j value, is 2 times j plus 1. And so this formula fits still, even though we have these half integer values and not just the integer values. Okay, and then we get the right number of states out of this. You can actually show really quickly in general that this will always be the case. If you let jt equal to L minus 1/2 or L plus 1/2, and then you add up the number of states that you would expect for L minus 1/2 plus number of states you expect for L plus 1/2, this will be 2 times L minus 1/2 plus 1, and then plus 2 times L plus 1/2 plus 1. And now if you add all this together, you'll get that this is equal to 4 times L plus 2, which is exactly equal to g of L times g of S, which is 2L plus 1 times 2. Now, finally, the only case where you have to watch out is for s orbitals. Right? So when L equals 0, you have that L minus 1/2 absolute magnitude is equal to 1/2, and then L plus 1/2 is also equal to 1/2. And so in this particular case, this is why it's important to draw this with a magnitude, is that these both give you the same one. These both give you the same jt value, and so you only use one of them. And this makes sense now because we have the number of states for a jt equals 1/2 would be 2. And if we started with L equals 0, that's only one angular momentum state. And then we have for S equals 1/2, that's 2 states. So this would be 1 times 2 has to equal 2. If you had both of these as allowed values of j, then you would have more j states, right? There'd be 2 from here, 2 from here, but there's only 2 from the L times the S part. Okay, so that is how you add angular momentum, at least in the special case that we're dealing with, where we're always going to add an integer angular momentum with an angular momentum of 1/2. In the next video, we'll introduce what are known as term symbols, which are convenient ways to express all this detailed information for atoms in a way that you can easily read off the selection rules.